Welcome to the explainer. So imagine trying to find a needle in a digital haystack. You've got this massive database of millions of records, and you urgently need to locate just one specific name, one specific ID, or one specific number. How does a computer actually pull that off without just freezing up for hours? Well, today, we're going to explore the absolutely fascinating world of computer search algorithms. We'll look at how computers sift through mountains of data and how a remarkably simple shift in strategy can turn a painfully slow process into a lightning-fast one. Okay, let's dive into this. Pretty much every application you use today relies on lists or arrays to store massive amounts of data. From your phone's contact list to the global databases of multinational tech giants, organizing this data is completely foundational. But storing the data is really only half the battle. The immediate real-world problem we face every single day is how to efficiently find a specific record within those massive lists. Because if our search method is poorly designed, honestly, it doesn't matter how fast the computer's processor is. The whole system is just going to bog down. Here is our roadmap for today. We'll be covering organizing data, the standard linear search, optimizing that search, real-world examples, and finally, the highly efficient binary search. All right, let's kick things off with part 1. Organizing and finding data. And that flows right into part 2, unsorted data and the linear search. The absolute most fundamental concept you need to grasp right out of the gate is that the state of your data dictates your entire strategy. Think about it. If you just dumped a bunch of paper files on your desk without alphabetizing them, how would you find a specific one? Your natural intuition would probably be to just start at the very beginning and look at each file one by one until you spot the one you need, right? Well, in computer science, this intuitive baseline is called the linear search. It's an algorithm that searches a list starting from index 0, moving sequentially, one by one, until the target is found or the list just ends. Because it checks every single position in exact order, it requires absolutely zero pre-organization. That's exactly why it's the go-to method for searching through completely unsorted datasets. It's simple, it's a bit naive, but hey, it gets the job done. Now, what's really interesting is how this physically plays out in an array of test scores. Let's say our target is a score of 97. The algorithm has absolutely no clue where 97 is, so it has to start at index 0, which holds the number 79. Not a match. So it literally jumps to index 1, then index 2, index 3, and finally hits index 4, where it finds our target of 97. It took 5 distinct steps to find the data. If you map this logic over to Python code, it's actually quite straightforward. We take our target input, and we set a variable called found to false. Then we use a basic for loop to iterate through every single index in the list. If the target matches the item at that index, we just flip our found variable to true. But wait, here is the critical flaw in this specific approach. A standard for loop will just keep going. It's going to check every single remaining item in the list, even after it has already found the target. Imagine having a million items and finding your target at index 4. This code will unnecessarily check the remaining 999,995 items. It is literally incredibly wasteful. Which brings us nicely to part 3, optimizing the linear search. The big question we have to ask ourselves here is, why keep checking if you've already found it? The solution is to introduce an absolutely crucial programming habit, the early exit. Instead of a for loop, we bring in the while loop. By using a while loop with a dual condition, we tell the program to keep searching while we haven't reached the end of the list and while our found variable is still false. The very microsecond found becomes true, the loop breaks, and the program instantly stops searching. So the crucial point is when you compare the runtimes. If our target is 79, which happens to be at the very front of a 10-item list, the old for loop still runs 10 times. But the new while loop, it runs exactly 1 time. That right there is our best case scenario. However, think about this. If our target is 100 and it doesn't even exist in the list, both loops are going to run 10 times. This perfectly introduces us to the dreaded worst case scenario in computer science, where the algorithm is literally forced to check every single item in the entire dataset. Let's move on to part 4, real-world search examples. Let's see how this actually scales up in practice. Imagine you're hosting a huge webinar. You have a registration array containing 500 participant usernames, and they're completely unsorted. It's just a random list of people who signed up over the last month. A user logs in, and your system needs to instantly verify if their username is registered in that array. Assuming the username is actually on the list, how many evaluations will your program have to make? Well, on average, it's going to take 250 searches to find them. Half the time it'll be faster, half the time slower. But remember that worst case scenario we just talked about? If someone types in an unregistered username, your poor program has to painstakingly evaluate all 500 names before it can finally say user not found. Now just imagine for a second that list isn't 500 people, but 500 million people. That linear search suddenly becomes a massive, crippling bottleneck for your entire application. And this brings us to a major pivot in our narrative, driven by one really simple question. What if the list is already sorted? If we actually take the time to organize our data in ascending order first, it opens the door to an ultimate optimization strategy that changes the rules of the game entirely. Which leads us to our final section, Part 5, Sorted Data and the Binary Search. Now, this is an incredibly elegant, highly evolved algorithm, but it comes with a strict prerequisite. Your data absolutely must be sorted in ascending order for this to work. But if it is sorted, we no longer have to check items sequentially. Instead of starting at the beginning, the binary search physically jumps straight to the middle of the dataset. Step 1, compare your target to that middle item. Step 2, because the list is sorted, if your target is smaller than the middle item, you instantly know it cannot possibly be in the upper half. Boom, you just eliminated half of your massive haystack in a single guess. Step 3, you take the remaining lower half, jump to the middle of that, and narrow the search range again. Step 4, you just repeat this halving process over and over until you either land exactly on your target or you narrow it down to one final item. It's brilliant. And this brilliantly illustrates how we code this up in Python. We use pointers called start and end to define our search boundaries. We calculate the midpoint by simply adding start and end and dividing by 2. If our target is less than the middle item, we dynamically shift our end variable to be just below the middle. If it's greater, we shift our start variable to be just above the middle. The search window rapidly collapses. Instead of checking 500 items in our webinar worst-case scenario, a binary search would find the answer in a maximum of just 9 steps. It absolutely crushes the worst-case scenario. No contest. To summarize this epic contrast, let's put them head-to-head. The linear search is your reliable but somewhat slow workhorse. It works on unsorted lists by checking sequentially, but it suffers from a highly inefficient worst-case scenario. The binary search, on the other hand, is your high-speed bullet train. Yes, it requires the upfront work of sorting the list, but by having the data at every single step, it remains highly efficient no matter how ridiculously large your dataset gets. Which leaves us with this provocative thought as we wrap things up today. In our modern digital landscape, our data haystacks are growing from thousands to millions to billions of items. When efficiency is literally everything and processing power costs real money, can you really afford not to sort your data? Understanding the sheer power of algorithms like the binary search is the very first step to writing code that doesn't just work, but scales beautifully. Thanks so much for joining me on The Explainer today, and keep questioning how your data flows.